Okay, hi everybody. Welcome to New England Dynamics and Number Theory seminar. Today our speaker is from Rutgers, which is this time not far from New England. And the title is, so the speaker is Chris Lutsko, and the title is Spectral Approach to Counting and Equidistribution Problems. Welcome.
All right, well, thank you very much for the opportunity to speak, and let me thank the organizers again for organizing this seminar, which has become a staple of the week now. So this is a number theory and dynamics seminar, and my research tends to focus a little bit more on the number theory side of things. But towards the end of the talk, I've thrown in a dynamics application for people. So that's your motivation to stay awake for the end of the talk. I want to focus for this talk more about a method than any individual results. And it's a method for counting points in group orbits. This is a very common problem that arises in numerous contexts. And we have some very strong tools for understanding these types of problems. So to start with, I'm going to focus on a sort of example, a warm-up problem, which is very well understood, which is the Gauss circle problem. I'm not going to say anything overly dramatic about it, but hopefully this should be familiar and it will give us the idea of where we're going. After that, I'm going to introduce this classical problem called the Apollonian or Kleinian counting problem. And then we're going to need to take a slight technical detour to talk about some spectral theory on the upper half plane or upper half space. After this technical detour, then we'll be in a position where we can generalize the Gauss circle problem, and I'll explain what I mean by this. And then finally, we can return to the Apollonian counting problem, and I can tell you some theorems in that context. And I'll say a word about the proof. And finally, this is the more dynamicsy aspect of my talk, which is a recent or a work in progress, which is an application to horospherical equidistribution. So I know we have some experts in the room, so hopefully I won't embarrass myself. Okay, so this is quite a lot, so let's get started. And let's get started with my warm-up problem, which is the Gauss circle problem. So here's the man himself, and in 1834, he studied the following problem. How many lattice points are there in a circle of radius r? So here we're talking about the integer lattice, and you have a circle of radius r, and you want to count the points which are entirely contained within the circle. So mathematically, he's looking for pairs x and y in z squared, such that x squared plus y squared is less than r squared, right? And he finds that the main term comes from the area of the circle, pi r squared, and the error term is bounded by the size of the circumference, so it's about size r. His proof is fairly simple, so why don't we see it? Here's my circle, and here's my integer lattice. You can encase every lattice point in a box which is entirely contained inside of the circle I've colored blue, and if it's on the boundary of the circle, if it intersects with the boundary of the circle, I've colored it red. So the true count is upper bounded by the blue and the red boxes, by the area of the blue and the red boxes, and it's lower bounded by the area of the blue boxes. And now we can get estimates for the number of boxes for this area by placing circles inside of the blue region and inside of the red region. So the inner circle gives us a lower bound and the outer circle gives us an upper bound. And together we get our asymptotic. You can figure out what the constants are. There's some square root 2's popping up, but at this stage, it should just be an exercise. Okay, so that's Gauss's proof. But he actually conjectured that the true error term should be slightly larger than r to the half. This is because even when we do this box procedure, some of the red squares, the lattice point is inside the circle, and some of the red squares, the lattice point is outside the circle. So what progress do we have on the Gauss circle problem? Well, this is a very big problem, which is very important. And we can't say that much about it. We can say that the exponent in the error term is larger than a half, certainly. And we can say that there's an upper bound, which is about 0.63. The lower bound comes from Hardy and Landau, and I think Voronoi also had some work on this. And the upper bound is very recent, 2017, coming from Bourgain and Watt. Now, Bourgain and Watt are going to exploit some very particular arithmetic structure, and their proof uses some L functions, which I don't want to go anywhere near today. So instead, I'm going to be focusing a little bit more on this approach by Hardy and Landau, which was also the approach used by Huxley in 2000 when he gets an upper bound of 0.629 as opposed to 0.627. So you can see that we're really making very slow progress on this problem. Yeah. So I want to say a word about the proof, which this argument really stems from work of van der Korpit, but it's also it's used by Hardy and Landau and then also Huxley. And the standard approach is the following. So we have our count, n of r, and we're going to write n of r as the sum over lattice points. This is my group orbit, by the way. And then we're going to insert a characteristic function of the ball. So if you're inside the ball, you have mass 1, and if you're outside the ball, you have mass 0. Now, we want to do spectral theory, which here means Fourier analysis. And in order to do Fourier analysis, you can't have, well, you don't have good convergence properties if your function is not smooth. So the first step now is to smooth. So we let psi be a unit mass bump at the origin, which is supported in the ball of radius epsilon. And in order to have unit mass, we normalize by this epsilon squared. And then the standard trick is to mollify, convolve the characteristic function with this epsilon bump function. Now my true count is upper and lower bounded by this epsilon count. So now that we have smooth functions, we can apply the Poisson summation formula, which gives us a way to move from the geometric side to the spectral side. So the Poisson summation formula tells you that if you have a sum over an integer lattice of a function, then that's the same as the sum over the Fourier, sum over the integer lattice of the Fourier transform. So that's this line here. Now we have the Fourier transform of a convolution, which is the product of Fourier transforms. And then it's an exercise to show that the main term comes from the zero frequency contribution. And then the whole game is to use Fourier analysis and exponential sum estimates to bound the second term. Okay. I'm not going to say much about this last step. This is the whole art of this, but for me, it's more important how we move from this geometric side to the spectral side. That's what I want to emphasize today. Okay. Now let's move on to the second classical problem for today. You know, every good talk should feature either Gauss and Euler and some Greeks. So here's our Greeks. or I guess Apollonius of, I guess, Turkish by modern standards, but anyways. So Apollonius of Perga from around 200 BC, he's very well known for writing his book on conic sections. And one of the things he studied a lot was the tangencies between these conic sections. And he had the following theorem. Suppose I have three circles, C1, C2, and C3 in this diagram, which have mutually disjoint interiors and which are all tangent to each other. Then there exist two additional circles, C0 is this outer circle, and C4, which is this inner circle, which are tangent to all three. A technical point, we think of the interior of C0 as being, outside this diagram, so out here. But in any case, so his theorem is this existence theorem about these two extra circles. Following this, René Descartes, in a letter to Princess Elizabeth of Bohemia, decides to study the radius of these different circles. And it's slightly more convenient, instead of working with radius, to work with the bend, which is the signed inverse radius. So my outer circle here has negative radius because its interior is outside. And the theorem that he comes up with is the following. Suppose I have three circles which are mutually tangent. And then from Apollonius's theorem, we have this fourth circle, C4. Then the bends of the four circles satisfy this quadratic form. So 2 times the sum of the bends squared is the sum of the bends all squared. So in particular, this tells you if you know the radius of these three circles, then you can find the radius of the interior of C4 and C0. Right, it's a quadratic equation, so there are two solutions. Okay, and we're going to call this the Descartes quadratic form. Okay, after this, in the 17th century, Leibniz takes this idea of these Descartes configurations, and he starts to generate infinite packings. So he starts with this configuration of 4 circles, and he starts to fill in the gaps. So if I have 3 circles, then you can fill in the gaps here, and then you can take any 3 in this configuration, you can fill in the gaps here. You can take these 3, fill in the gaps here. And you can keep doing this. You can do this as often as you like. And I think it's worth noting that this is a really early precursor to the modern idea of fractals. So I think Sierpinski was doing his work right around the turn of the 19th century. And this is obviously in the 1600s. So I think it's worth highlighting. And then the last, this talk has a lot of name drops, but the most surprising one is this chemist, Frederick Soddy, who won the Nobel Prize in chemistry for work on radiation, radioactive decay. And he, I guess once you win your Nobel Prize, you can do what you like. So he publishes a poem in Nature where he rediscovers or rederives Descartes' formula. And he notes that there exist infinite packings such that all of the bends are integral. Now, obviously, this isn't obvious because the Descartes quadratic form is a quadratic form. So you might expect to see some square roots popping up, but there exist integral packings, is Soddy's contribution. Okay. So this is where the number theorists start to get interested, because now you have a quadratic form and you're looking at integer solutions of that quadratic form. So to get a bit technical for a minute, a packing for this talk is an infinite collection of round disjoint balls whose union is dense in the end sphere. So all I've done here is I've stereographically projected R2 onto the 2 sphere. And you can see here, it's very obvious that my balls are dense, or if I take their, the balls are dense on this sphere. And we call such a packing Kleinian if it is the residual, if the residual set, so that's the bit that you get after you remove all of the interiors of the ball. So that's the kind of fractal structure. If that residual set agrees with the limit set of some discrete geometrically finite subgroup. And I'll explain a bit more what these words mean. And here's an example of a Kleinian packing, or sum of a Kleinian packing in dimension 3. So the outer sphere has radius 1/11, and then the inner spheres, their radius or their bends are annotated. So, okay, so what is the Kleinian or Apollonian counting problem? Well, suppose we have a packing in n dimensions. Let's let B of S denote the bend, remember inverse radius, of a sphere. The Apollonian or Kleinian counting problem asks, how many spheres are there with bend less than t? And can we get some asymptotic count for n of t? Okay. The last thing I want to highlight before moving on is that there's actually secretly a group structure in these packings. So I'm going to start with my initial configuration, and I'm going to maybe add one more ball, this one here. And now I can construct what's called the dual cluster. So the way to construct this dual cluster is to take any 3 tangency points in this initial configuration and connect them using a circle. So if I do this, I get these 4 circles, which I call my dual cluster. And it turns out that the full packing is the orbit of the initial packing under the action of the dual cluster. So you can see here, if I take circle B and I reflect it through circle D, I should get circle A. So there's secretly some group structure underlying this whole process. Okay. Yeah, so to generate the packing, we consider the orbit of the initial configuration under the action of reflections through the dual cluster of packing. Yeah. Okay. Are there any questions? Please feel free to ask questions at any time. Okay, great. So now I need a little bit of background on hyperbolic geometry and spectral theory. So let's let Hn+1 be hyperbolic n+1 space. So we have n coordinates, which are just real numbers. And then we have y, which is bounded below by 0. And then there's this volume element dv, which is the Euclidean volume element divided by y to the n+1. So for the upper half plane, here's my expert drawing of the upper half plane. The point is, if you have 2 trajectories, then up here at infinity, they're converging, and then down here towards the boundary, these straight lines are diverging because the 1/y blows up. Okay. we're going to let delta denote the hyperbolic Laplacian. So this is the Laplace-Beltrami operator or the Casimir operator, depending on your language, coming from the hyperbolic metric. So it's the standard Euclidean Laplacian. Then you multiply by y squared, and you also get this extra term here, depending only on y. And then the last thing I need is that the group of isomorphisms of Hn plus 1, I'm going to denote G. And for example, when n is 1, then G is just SL2R, so matrices with determinant 1. And when n is 2, this is SL2C. And for anyone who hasn't seen this, if I have a point here in H, call it Z, then a matrix G, which is A, B, C, D, sends Z to GZ, where GZ is AZ plus B divided by CZ plus D. So these are the standard Mobius transformations, and they give you an action of SL2R on the upper half thing. Okay. Now we're going to be concerned with discrete subgroups. So here I've drawn a discrete subgroup. This is a Hecke triangle group, which is generated by the matrix 1, 3, 0, 1. So this identifies this vertical wall with this one. This is a translation by 3. And then there's also the matrix 0, 1, minus 1, 0. These generate the group, and this matrix identifies the unit circle with itself. So this reflects through the unit circle. So here's my discrete group. And if I have a point in my space, I can look at the orbit of that point under the action of the discrete group. So here I have Z, and I've taken its orbit under some of the discrete group gamma. Now you can see that these orbits start to collect along the boundary. And a very important object in this theory is the limit set. So the limit set, which we typically denote by lambda of gamma, is the closure of the set of accumulation points of any orbit. It doesn't matter which orbit you take. It's invariant under the choice of orbit. And this is where fractals start to come into play, because the limit set, so if gamma is a lattice, then the limit set is just the entire boundary. But if gamma has infinite volume, then the limit set is some sort of fractal. So for example, with this example, you can see that this has infinite volume because we're picking up these pieces of the boundary. If I glue this together, I'm going to get a manifold that looks something like this. There's these two big funnels, and then there's a little cusp up here at infinity. So this is an infinite volume discrete group. And the limit set for this infinite volume discrete group is going to be some sort of Cantor set, because every time I get a funnel, I can cut out a piece of the boundary. Is there a question?
I'm not sure. Any questions?
I was hearing some noise. In any case. So suppose we have a discrete geometrically finite subgroup gamma, then we can consider the manifold, which is obtained by quotienting the upper half space by gamma. And we can consider the Laplacian acting on this L2 space. So this is a Hilbert space, and we have an operator. So if we have a Hilbert space and an operator, then we have a spectrum. The spectrum is everywhere where this operator doesn't have an inverse. So in particular, any eigenvalue belongs to the spectrum, but there are also points in the spectrum which don't come from eigenvalues. Okay, we're not going to be doing that much hard spectral theory, but we just need to know that there is a spectrum. And we know some things about the spectrum. So in this setting where we have a discrete geometrically finite subgroup, we know some things about the spectrum. First of all, the Laplacian has discrete spectrum below n over 2 squared. So here's n over 2 squared. Here's 0. So we have some discrete eigenvalues down here. And then we have continuous spectrum above n over 2 squared. So this whole region is contained in the spectrum. The base eigenvalue is given by delta n minus delta, where delta is the Hausdorff dimension of the limit set. So again, if gamma is a lattice, then the limit set is the whole boundary. So that means delta equals n, which means that this base eigenvalue sits here at 0. And this should be obvious because the constant function is an eigenfunction of the Laplacian if you have finite volume. But if gamma is not a lattice, then delta is going to be larger than 0. And it's going to be the Hausdorff dimension of the limit set, and the base eigenvalue is something coming from this Hausdorff dimension. So there's this interesting connection between the spectral side of things and this fractal geometry viewpoint. Okay, so that's what we know about the spectrum for a general discrete geometrically finite subgroup. Maybe I also need non-elementary, but anyways. So how do we actually exploit the spectrum? Well, in the Euclidean setting, I've already shown you how to exploit the spectrum, which is the Poisson summation formula. This gives us a connection between the Fourier, between the geometric side, which is just summing the function over lattice points, and the spectral side, which is summing the Fourier transform of the function over lattice points. Now, why do I call this the spectral side? Well, note that e to the 2 pi I n is an eigenfunction of the Euclidean Laplacian. And so when you're taking a Fourier transform, all you're doing is you're projecting onto an eigenspace. Right? So this is connection between the geometric side and the spectral side. So if I have finite volume, hyperbolic manifolds, then Selberg told us how to move from the geometric side to the spectral side, and that's via the trace formula. This is necessarily more complicated than the Poisson summation formula because the spectrum of the Laplacian is a lot more complicated. You have these discrete points, and then you have the continuous spectrum. So it's much more complicated in the hyperbolic geometry side of things. But nevertheless, we have this connection, and the connection is explicit between the geometric side and the spectral side. In infinite volume, we lack an explicit spectral decomposition. There are some attempts to come up with it. I think Borthwick has a book on this subject, but really there's no usable explicit spectral decomposition like we have in finite volume. And I don't think there's any hope for getting one. But what we do have is the following theorem, which comes from just abstract operator theory. So you can read in Rudin's function analysis, this theorem shows up. And it says, it actually says, suppose you have some operator L, which is self-adjoint acting on a Hilbert space. So it's a really general theorem, but for us, I'm going to specialize to where this is delta and this is the L2 space. And what it tells us is there exists a spectral measure on the real line and an operator, which sends the L2 space, the geometric L2 space, to the spectral L2 space. And it satisfies some properties. So the first property is the Parsifal's identity. So if you take an inner product on the geometric side, this gives you an inner product on the spectral side. So this is how you move from the geometric side to the spectral side. The second property is that the spectral operator plays nicely with the Laplacian. So the Laplacian is diagonal with respect to the spectral operator. So if I take the spectral transform of Laplacian of phi, this is lambda times the spectral transform of phi. And the last property is that if you have a point in the discrete spectrum, then the value of the spectral operator at that point is just the projection onto that eigenspace. So here I've assumed that my point has multiplicity 1, and you can get into some trouble if the multiplicity is infinite, but this is enough for today. Okay, so now we don't know anything about the spectrum. We don't have an explicit spectral decomposition, but we know that there is a spectrum. We know how to get there, and we know that the Laplacian plays nicely with the spectral transform. And it turns out that's enough. And like I say, this applies in general to a self-adjoint operator. If you're working with Lie groups, then this is sort of equivalent to talking about the unitary dual and not Parsifals, but the Plancherel theorem, which I think is for non-compact Lie groups is due to Harris-Chandra. And then Schur's lemma, which tells you that elements of the Casimir elements act via scalar on the unitary dual. But anyways, so moving on, let's talk about some applications to this spectral theory. So one application is to hyperbolic lattice point counting. So the problem is the following. Suppose we have 2 points, Z and W, and I'm going to take the gamma orbit of Z. So these are the black points. This is gamma of Z, this is my orbit. And I want to count the points a distance t from W in the gamma orbit of Z. So I want those gamma Z's whose distance from W is upper bounded by t. So you're counting points in a circle, but now it's not Euclidean centered, it's hyperbolic centered circle, right? So that's why this distance doesn't look the same as this distance. And you might think maybe we can do the same thing as Gauss did, right? Maybe we can estimate the interior of this ball, and we get some error term coming from the boundary. This is doomed to fail because a unit neighborhood of the boundary has the same area as the ball. Most of the area of this ball is down here, and notice that most of the points are down there. So this, at least Gauss's purely geometric approach is going to fail. But maybe we can apply the approach of van der Korpen and Hardy and Landau and all of those people. And before we get to that, note that this is where the number theory comes in. If both of my points are at I, then you're counting elements of gamma such that a squared plus b squared plus c squared plus d squared is less than t. Okay, so you're really counting points along a group orbit such that some quadratic form is bounded. I'm going to rattle off some results, and in order to do that, I need the following notation. If I have a discrete eigenvalue, then it's more typical to work with Sj, where Sj solves this equation. Lambda j is Sj n minus Sj. So Huber, Patterson, and Selberg had the following theorem, that for a finite volume group, this hyperbolic lattice point count is given by terms coming from the discrete spectrum, which have size t to the sj, and then an error term of size t to the 2/3. So the dominant term, because the base eigenvalue we know is at 0, the dominant term is just t. And we know what the constant is. And this generalizes for all dimensions in large generality. Okay. In infinite volume, and this exploits, or one way you can prove this is to use the Selberg trace formula. Huber and Patterson use the pre-trace formula, but never mind. But in infinite volume, we don't have a trace formula. So this is why Lax and Phillips introduced this abstract spectral problem, or abstract spectral approach. So now we're taking geometrically finite, which just for today's talk, geometrically finite just means not too big. Group with critical exponent larger than 1/2. Then for t large enough, we have the same asymptotics. So we pull out the same dominant terms coming from the discrete eigenvalues, and then an error term, which is like t to the 1/3 plus the Hausdorff dimension divided by 3. So the dominant term here is going to be t to the delta, where delta is this Hausdorff dimension. And this generalizes to all dimensions as well. A related problem is, what if your observer is at infinity? Then you're counting points above this line. But that doesn't make sense if you have a stabilizer at infinity. So let's just count points in a strip. So now you want to count points above size 1/t, which is equivalent to counting group elements with c² plus d² less than t. And first Alex Kontorovich and then Kontorovich and myself proved the following asymptotic. So again, you pick up all of these dominant terms coming from the discrete spectrum, and then you get an error term coming from the continuous spectrum. Okay, so we have these very accurate asymptotics for these counting theorems. And for example, if you want to count Pythagorean triples, whose norm is less than t, then this kind of asymptotic will give you a very sharp error term. Not sharp, but very precise error term. Okay. Let's move on to the Apollonian. Before I talk about proofs, let's move on to the Apollonian case. So here, I've drawn the dual cluster. So these are the dual circles in that group that generates the Apollonian packing. But I've drawn them in the boundary of H3. And I've placed a geodesic hemisphere on top of this, on top of each circle. And now if you take the orbit of a point, I'm not sure how much you guys can see this, but the limit set is down here, and it's exactly the Apollonian packing that you started with. So really, these Apollonian packings kind of live in the boundary of H3. And the group gamma is a group of isometries in H3. So you can contextualize this problem in hyperbolic dynamics. What do we know about the spectrum of the Apollonian group? Well, from work of Lax Phillips and Patterson Sullivan, we know that there's continuous spectrum above 1. We know that we have this base eigenvalue, and then there's finitely many discrete eigenvalues. From work of Boyd and McMullen, we know what this Hausdorff dimension is, or approximately we know what it is, which tells us what the base eigenvalue is. There's a conjecture of Sarnak's that these other eigenvalues, other than the base, don't exist. So there's really just the base eigenvalue. And I'm pleased to say that in work in preparation with Duby Kelmer, who I see is in the audience, and Alex Kantorovich, we were able to prove this conjecture of Sarnak. So we really understand the spectrum of these Apollonian packings as well as one could hope. There's a base eigenvalue, which is approximately 0.9. Then there's a big gap, and then there's the continuous spectrum. Okay. Now, using the abstract spectral approach of Lax and Phillips, Alex Kantorovich and I were able to improve on some theorems of Boyd, Kantorovich, O, Vinogradov, Lee, and O. That for any, there's a technical assumption here, Kleinian packing, assuming there are no eigenvalues other than the base, we get the leading term is t to the delta, and then we get this error term, which it's not very important, but the important thing is that it's an improvement in the error term. If we have eigenvalues other than the base, then the error term just gets worse. Okay. So we understand, a lot about these Kleinian packings, and we have a relatively sharp asymptotic. Yeah. So let me sketch the proof. And the proof that I'm going to sketch is the proof where you're counting orbit points above height 1/t. So we want to count the elements gamma in this orbit modulo the stabilizer of infinity, such that c² plus d² is less than t. And the way to do that is we're going to take the same approach as we talked about for the Gauss circle problem. We're going to define our count as a sum over the group elements of the indicator function that whatever you want to happen actually happens. And we're going to add in this parameter g such that now we have a continuous function, and note that the true count is f of t evaluated at the identity. Now we need to smooth f because otherwise we can't do spectral theory. So we introduce an epsilon mass around the origin, and we automorphize it, and then we take this inner product between ft and our automorphized smoothing function, psi. And again, we're going to be in the situation where nt is upper and lower bounded by nt tilde. So here's my bump functions. This is some sort of smoothing procedure, and this is kind of the correct way to mollify when you're working on quotients of hyperbolic space. But now we have an inner product. So we can apply Parsifal's identity, which gives us an inner product on the spectral side. Now we know what the spectrum looks like. We have these discrete values, which will give us our main terms. And then we have the continuous spectrum, which gives us this integral. And then there is a sort of harmonic analysis, spectral analysis method developed by Lax and Phillips, and then sort of strengthened by myself and Alex, which allows you to estimate each of these terms using the Laplacian. And this comes from the fact that the spectral transform plays nicely with the Laplacian. So this allows us to pull out all of our dominant terms, and we get this error term, which goes all the way up to the continuous spectrum. So this error term in some sense is optimal, but the problem is that we've smoothed with epsilon, and these epsilons are going to play against this epsilon. So the last step is to optimize by finding a choice of epsilon. So, okay, that's a very rough sketch of this proof. The next thing I wanted to talk about is my dynamics, my nod to the dynamics community.
Excuse me, Chris. So, sorry.
Yeah.
So this, so just a historical question. This proof is due to whom? Say for hyperbolic space.
I guess Lax-Phillips, yeah.
Lax-Phillips, okay.
The abstract spectral proof is due to Lax-Phillips, yeah. The explicit spectral proof, I guess, you can go up back to Huber in the 50s. But there he's really using the explicit spectral decomposition. Here we're using very little about the actual group. We're using very little knowledge, just the fact that we have an operator and an L2 space. That gives us this abstract spectral theorem, which I cited before. Yeah. But yeah, this goes back to Lax-Phillips in 1982. So, so what I've shown we've shown is that there's this spectral methods, which are very good at deriving these counting theorems. They give us very sharp error terms. And in some sense, they're very soft. They don't require a lot of information about the group. There's another method, which is to exploit dynamical equidistribution theorems. So these are things like horospherical equidistribution or Ratner's theorem. These are also able to derive counting theorems. But they have a tendency to be quite finicky, and the setting is very important in these equidistribution theorems. And making them effective seems to be quite a difficult problem. The upshot is that dynamical equidistribution is a very powerful tool. So there's all of these other applications which you can use dynamical equidistribution for, which I think there are some experts in the audience who would say a lot more than I can about this. But things like Diophantine approximation, counting theorems, sieve applications, and other things. So the hope is maybe we can use these spectral methods to actually derive the dynamical equidistribution theorems. Maybe we can get a new proof of some dynamical equidistribution theorems, which gives stronger error terms, which is sort of automatically effective, and which is very soft, uses very little explicit information about the group. And in a work in progress, I can say that the answer is yes, you can take this Lax-Phillips method and apply it to horospherical equidistribution. And I think more generally other equidistribution problems, but it's very early days. So the example which I want to talk about is, suppose we have, let's just work with SL2R, and this does generalize to SLNR. And suppose we have some geometrically finite Zariski dense discrete subgroup. And let's assume that the Hausdorff dimension is larger than a half. Let's assume that there's also a non-trivial stabilizer of infinity. I don't think this is necessary, but at least in my first application of this method, it is necessary. And we can assume by scaling that the cusp has width 1. And now we're going to take a function. Here's my function. We're going to integrate out the x direction, and we're going to have it sit at height 1 over t. So the point is that we have some group, and we have some horosphere, and we have a function that we're integrating along the horosphere. As we push the horosphere down, this should equidistribute over the space, and maybe we can get some asymptotic for this horospherical average. There's some very nice animations on Alex's website. So you can see here is my horosphere. Oh, I can't write on this, but anyways. Here are some horospheres, and they're being pushed down, and then they're equidistributing as they're getting pushed down. So thanks to Alex for having those on his website. So what can we say about this horospherical average? Well, the theorem is the following. If f is a k invariant function, so it lives on the half space and not the tangent space, although you can lift this theorem up to non-k invariant functions. Then this horospherical average is asymptotically equal to t to the delta minus 1 times a constant. And this constant is given by the base eigenvalue, the integral of f, the inner product of f, with the base eigenfunction, which comes from Patterson-Sullivan theory and is explicitly known. So we get this error term. Then we get all of these contributions from the discrete spectrum. And then we get an error term, which comes from the continuous spectrum. This generalizes to higher dimensions. There's a technical assumption that I don't know how to deal with the complementary series representations, so we're just going to assume those aren't there, which is true. And they don't play a role when n is 1 or 2, but in higher dimensions, we don't know how to deal with those. And we don't need to assume f is k invariant. So we could actually work on the tangent space as well as the upper half space. And this improves in the error term on work of Li O and Mohammadi O, which is quite recent. I think part of the achievement is that this proof is really, maybe 10 pages, whereas these dynamical proofs require a lot of very fine analysis, which is very detailed and very impressive, but finicky. Okay, I have 10 minutes left, so maybe I can explain a little bit about the proof of this horospherical average, because I think maybe for some people that's the most interesting. So why don't I move to my notes? So we want to understand the integral. What is this? We want to understand the integral, the horospherical average. And again, the first step is to smooth. So we're going to let psi be an epsilon bump function, depending on t of y. So this is a bump of size epsilon over t squared around 1 over t. So the point is we don't like discrete stuff. So we're just going to place a little bump in this tiny little region. It has mass 1 in the hyperbolic metric. And then we're going to let psi, capital Psi of x plus iy be the automorphized, the automorphization, I guess you can say, of this little psi. And now my epsilon thickened mass, or average, is the inner product of f with psi. We can pass to the spectral side using Parseval's identity. And then we can extract all the lower order terms just by decomposing this inner product, or all the higher order terms, I should say, like this. And then we get a term coming from the continuous spectrum. And then the whole game is to use the Laplacian and use these spectral transforms to estimate these various terms using the usual Lax-Phillips machinery. Okay, so maybe I should stop there. And first of all, I should say some credit is due to Alex Kontorovich for the images and also Ivan Raskin for this image. But yeah, maybe I should stop there and ask if there are any questions.
Okay, well, let's thank Chris, first of all, before asking questions. By a little round of applause. And then, yeah, any questions? So let me ask something. Usually when people are studying horospherical equidistribution by methods like in Gauss papers and some of the precursors, what happens there is that there is some information about mixing, and then mixing is used to say something about equidistribution of horocycles. Right, and probably it goes back to Eskin McMullen and later papers. But and then now you are saying so what Lee or Mohammadi were doing is that they have some estimates for the speed of mixing, and then they use those to have estimates on equidistribution. And now you are saying that you can improve the estimates for the equidistribution. Does it mean that you have some extra information on the speed of mixing?
So I can bypass the speed of mixing.
Yes, but can you go back in this?
Can we go back? Probably, because mixing is just again, you're just taking an inner product, so you can always unpack that inner product and using the spectral, you can use that inner product to pass to the spectral theory side of things.
So your result actually improves the speed of mixing, not just.
Well, I should be careful because Mohammadi O, I believe they get the optimal speed of mixing. They're able to get all the way up to at least all the way up to the first eigenvalue.
Okay.
And then their thickening procedures is where they lose a bit. So in terms of mixing, I don't know if I can improve on.
Okay, so that was my question. So I think the information is lost in this passage from mixing to equidistribution, which is exactly some kind of thickening.
Yeah, exactly. So the thickening is kind of, I guess, simpler in this case.
Okay. That's interesting. Other questions?
It's very early days, so I'd be interested to know what we can say about mixing. Maybe we could extract the higher order terms coming from the rest of the discrete spectrum, and then get all the way up to the continuous spectrum. But
so we means you and Alex?
No, this is a project I'm working on my own. Sorry, I use we sometimes. The royal we.
That's fine.
I have a question, which
the
same problem if you do go on for the lattice case, but you can also prove for spherical equidistribution in two different ways, either through the dynamics or using the spectral approach. Now, in the spectral approach, the only thing that comes up is somehow there is like the spectrum that comes from the Eisenstein series. You don't have anything else. And just my question is if you can somehow, is there something similar happening here, or here you just have, because there's no distinction here between the discrete spectrum.
Are you talking about the embedded discrete eigenvalues? The embedded eigenvalues, or
now, if you just apply your results but without knowing that your group is a lattice, right? Then you would still get the same result, but all your secondary terms would be all the exceptional eigenvalues of the Laplacian below the continuous spectrum.
Yes. And then an error term coming from the continuous spectrum, yeah. So that's what Selberg and Hooper and Patterson get. For a lattice.
This is for the horospherical equidistribution.
Oh, for the horospherical equidistribution.
What confuses me is that for the horospherical equidistribution, for the lattice case, you don't get contribution from all eigenvalues below the continuous spectrum as secondary terms, but just those coming from residues of Eisenstein series. So I'm trying to see if you just apply your general spectral argument there, where would those disappear all of a sudden?
I guess in these constants, the constants come from the projection onto the eigenspaces, and somehow those constants must be zero.
Yeah, it can be zero.
Yeah, the constants can be zero if you're somehow orthogonal to these eigenspaces, or I'm not entirely sure what happens. Yeah, in that case. To be honest, I say nothing about the constants other than that they exist. I should give a nod to, I guess, Sarnak and Zagye, who are able to get horospherical equidistribution, the lattice case, with a really almost optimal error bound. And this is because they're not thickening in any directions. So they're really using arithmetic properties. So they get some error term that comes from the prime number theorem and the Riemann hypothesis, which I can't get anywhere near to, but this only holds in arithmetic context in finite volume.
Thanks.
Yeah.
Other questions? Comments? Okay, well, let's thank Chris again. It was very nice.
Thank you.
And thanks to everybody for coming and keeping this staple in a good condition. We couldn't have done it